Hi everyone, we're going to learn about absolute value function today. Our essential question is how can functions be represented and translated in different ways? The parent function equation of absolute value function looks like y equal to absolute value of x. And we know that the meaning of absolute value function is the distance between the point and the origin. That means let's use this graph, this table, y and x here. And so this is what the function is doing to the values that is taking. Like if I give a value like a 1 to this function, it's going to give me 1. If I give 0, it's going to give me 0. If I give -1, it's going to give me +1. So it takes off the negative and gives a positive value to me. If I give -2, again, it will be +2. If I give +2, it's going to give the same thing, 2. So these are the values that I have. Now I'm going to use these points to graph the function. 0 and 0, 1 and 1, 2 and 2, -1 and 1, -2 and 2. So as you see, the y values are always positive, but the x values could be either positive or negative. So I'm going to use these lines to graph the function. Okay. Let me make it a little bit thicker. I like it more thick. Okay. So this will be the graph of absolute value function. So let's talk about some of the characteristics. What are the x-intercepts and zeros of this function? X-intercept is the same as 0, and we know that means where does the graph cross the x-axis? And as we see, that's this point, which is 0 and 0. What is the y-intercept here? That means where does the graph cross the y-axis? That's again the same point, which is 0 and 0. What is the minimum point here? What is the lowest point of this graph? It's this point again, 0 and 0. So this point is minimum point of the function as well. What is the maximum point? As you see, the graph is going to increase because we have arrows here on two sides. That means the graph is increasing forever. It's going to infinity. This means that our function doesn't have any maximum point. There is no specific point that I can say that this point is the highest point of all, because it's just continuing to increase forever. So there is no maximum point here. The vertex is this point. It's at the origin, 0 and 0. Axis of symmetry. Do we see any kind of symmetry on this graph? Yes, as you see, if I consider this line like the y-axis, which is also called, I'm going to use this line, this color, okay, y-axis, which is also called x equal to 0, the left side and the right side of the graph are mirror of each other to the x equal to 0. So that means we have a symmetry here, and axis of symmetry is x equal to 0. This function is continuous because if I put my pen on the graph and just try to follow the path from the beginning to the end, I don't have to pick up my pen and continue at any point. Like all the points are continuously going forward. So this function is continuous. Now, what is the domain of function? We know that for domain, we have to move from left to right and look for x values that are covered by this function. So as I move the left side, the most left point is an arrow. So that means it's starting from -infinity And the last point that I see again is an infinity because we have an arrow. And we always put parentheses around infinities. Now the range, we know that for range we need to move from bottom to top and look for y values. Okay, as I move from bottom to top, where do I start from? We start from the graph is starting from this point, which is 0. So the first y value that I see is 0, and because it's on solid line, it's included, so I put a bracket here. Then I continue moving up, and the last thing that I see are these arrows. That means it's going to continue to infinity. So this will be the range of my function. Okay, let's talk about the transformations. As we have talked about this before, I'm just going to review that. The general form of transformations that can happen to our function is this: plus and minus a times f of b times x minus h plus k. So if we have a negative outside of the function, that means we have a reflection over x-axis. That means like whatever point that I have on top is going to be reflected over x-axis and go like here, reflected over x-axis. If I have a value multiplied by function, and this value is something between 0 and 1, let's say, for example, 1 over 2, or I don't know, 3 over 4, something less than 1, we're going to have a vertical shrink. But if the number is greater than 1, let's say 2, 4, 100, whatever, something greater than 1, we are going to have a vertical stretch. So if we have vertical shrink, that means our graph is going to be wider and shorter, and we have vertical stretch, it's going to be taller and narrower. Next is the b value that could be multiplied by x inside of your function. So if this x is a value between 0 and 1, we're going to have horizontal stretch this time. So a value is, let's say, 1 over 2, or 5 over 6, anything like that, which is less than 1, we have horizontal stretch. If the value is greater than 1, we're going to have horizontal shrink this time. Then, as we see, we have a value which is subtracted from x. If this h is a negative value, we are shifting the function to the right. If h is a positive value, we're going to shift the function to the left side. Then, if we add a value like k to the function, like outside of the function, this is something is happening to y actually. So we're going to move the function either up or down. If the k is less than, it's a negative number, it's going to be shifted down. If it's a positive number, it will be shifted up. So these are the summary of transformations that could happen. Now we're going to do some examples here. Okay, here, this is my function, f of x equal to negative absolute value of x minus 4. So let's see what transformations do we see. We recognize that the parent function is y equal to absolute value of x. The transformations that I see here, one of them is this h value, which is a number, which is a positive number that is subtracted from x. So that means the function is going to move right for 4 units. So right 4. Other transformation that I see here is this negative value. This is basically, oops, sorry. So this negative value means that we have a reflection over x-axis. So I'm going to start graphing the function first. We know that the parent function looks like this, passes through 0 and 0, 1 and 1, as we did before, 2 and 2, negative 1 and 1, negative 2 and 2. and then the graph is going to look like this. Okay. So based on the transformations that we see here, this function should be moved right 4 and reflected over x-axis. So I'm going to reflect it over x-axis, and so this is reflection over x-axis and moved 4 to the right. 1, 2, 3, and 4. So this should be the transformed function, okay? So this is my prediction. I'm going to use my calculator to make sure that I'm doing all these right, okay? So I use my calculator here, and let's go. I'm going to go to y equal to, let me clear all these that I had from before. Okay, so for y1, I go second window and number 1, which is absolute value of x. So that's my parent function. And the second function, which is the transformed function, is negative absolute value of, so I use alpha window number 1, and then I'm going to write x minus 4. This is my second function. Now I can graph that, and as you see, it's exactly like what I had predicted before. Now I can even use my table here to find the values. Okay, so if I have, let's say, 0, y is negative 4. So I'm checking the red ones, that's y2, the second function, the transform function. So if it's 0, y is negative 4. X is 0, y is negative 4, which I don't, and let's use another number. I'm going to use something which is around this area. Okay, so if x is 1, y is negative 3. Okay, and if x is 3, y is 1. Okay, these points are good, so I'm going to use them. X is 1, y is negative 3, so it's going to be here. This is one of the points. X is 1, y is negative 3. Then if x is 2, y is negative 2. X is 2, y is negative 2. So it's here. X is 3, y is negative 1, and x is 4, y is 0. So x is 3, y negative 1, x is 4, y is 0, and 5 negative 1, 6 negative 2. So 5 negative 1 and 6 negative 2. I could just continue, but that is enough for me. I can use that to graph my function. Okay, so this will be the graph of my function, and as you see, it's reflected over x-axis and moved 4 to the right. So this is the graph of negative absolute value of x minus 4. Now let's go to next example over here. Okay. Again, the parent function is absolute value of x. So I'm going to use the points 1 and 1, 2 and 2, negative 1 and 1, and negative 2 and 2 to graph it. And this will be the graph of my parent function. Let me change it to blue color because I was graphing the parent functions in blue. Okay, so this is my parent function. Now, let's graph the transform function. First of all, we need to identify the transformations that are happening here. One of them is move right to 1 because we have a negative 1 after x. So this is right to 1. Then I have plus 4 after the function. So that will be up 4. Then we have 1 over 2 multiplied by function. So this is a value which is between 0 and 1. a number less than 1. So it's going to be a vertical shrink. So vertical shrink is happening here by a scale factor of 1/2. And then we also have a negative here, that is reflection over x-axis. So I have to move this function right 1, up 4, and shrink it by a scale factor of 1/2, and then reflect it over x-axis. I'm going to use my calculator to find the exact points here. So let's go to y equal to, the first one is what we have as the parent function. I'm going to clear the second one, and okay, so negative 1/2, and then we have absolute value of x minus 1, and after the function I have a plus 4 here. So this is the equation. Now I'm going to graph it. As you see, this is moved right 1, up 4, reflected over x-axis, and also shrinked by a scale factor of 1/2. As you see, the graph is kind of wider. That's why we have a vertical shrink here, wider and shorter actually. Okay, so let's use the points here. Second table. Okay. Um, so if I have -1 as x, y is 3. And I'm going to use the other one, 1 and 4. So -1 and 3, 1 and 4. -1 and 3 is one of the points. -1 and 3. The other one was 1 and 4, which is here. Okay, let's see what other points we can use here. If x is 3, y is 3. So I could use the other points as well, but this one, like 3, gives me a round number. That's why I use this one. So 3 and 3 is the other one. 3 and 3 is here. And basically, this is enough for me to graph my function. I'm just going to use the red color, which is already red. Okay, so I'm gonna graph it now. Okay, so this is a graph of the transform function. Okay, now I'm gonna use, I'm gonna find domain and range of this function. Domain of this function, as I move from left to right, we know that I need to move from left to right. I start from an arrow, that means it's from -infinity, and then I move to the right and it's going to infinity again because we have another arrow on the right side, so it's going to positive infinity as well. The range, I need to move from bottom to top. As I move from bottom to top, the first thing that I see from my graph, this red one, is the arrows, are the arrows that I see. So starts from -infinity again because I'm moving from bottom, and at topmost point, this point, which the y value of that is 1, 2, 3, 4. 4 is the last point that I see as I move from bottom to top. So that's 4. And I use brackets here because this 4 is on a solid line and is included. I also forgot to do the domain and range on the top one, so I'm going to find that one as well for you. Domain, I move from left to right. This arrow is the first thing that I see from left, so it's -infinity. And as I move to the right, again, another arrow is at the rightmost point of this graph, so it will be to positive infinity. Range of the function, I move from bottom to top. The bottommost point are the arrows that I see. So -infinity to the topmost point that I see from this graph, the red one, is this one, which the y value of this point is 0. And 0 is included because it's on the solid line. So I use a bracket. So this one is the range of this function. Okay. Now let's go to the next page. Over here, we have some questions that we want to answer. How can the rates of change of an absolute value function be determined? One of the ways that we can determine the rate of change is just visually see what is the rise over run. Let's say, for example, here I have this absolute value function. I just consider 2 points, like from this point to this point. What is the rise over run? And that will help me to find the rate of change. The other one is the slope formula. Just by looking at the formula of the graph, the equation, I need to find the coefficient of x that will be the slope of the function. So that's one of them. Also, the other one, the other formula for slope formula is like, let's say I consider these 2 points, x2 and y2, and this one x1 and y1. The slope formula is y2 minus y1 over x2 minus x1. This will be the slope of the function. So you can either find, if you're given the equation, by finding the coefficient, or if you have 2 points, you use this formula to find the slope formula. Also, the other way is to check the transformation of the parent function. That will also help you to find the rate of change of your absolute value function. Next, we have what kind of mathematical and real-world situations can absolute value functions model? One of them is distance versus displacement. Okay, I'm going to show you a really short, quick example here. Let's say we have a point like A here, B, and C. The distance between them is 100 meters. Okay, and I have a car here. I move this car, let's say from A to B. Oh, sorry. Give me a second. Let me fix this for you. Okay, so let's say I have this car and I'm moving this to this point. So as I move this point from A to B, I can say the distance that the car has been moved is 100 meters. So it's been moved to point B for 100 meters. The distance is 100. If I move it to point C, again, the distance is 100 meters. So that's the distance, but I can also add something else here. I can say I have moved the car to the right, or let's say, for example, to the east for 100 meters, or I moved it to the west or to the left for 100 meters. So when the direction is also involved, that's called the displacement. So we can use absolute value functions for real world situations that involve distance and displacements. Another situation could be maximum and minimum speed limits. So we can also use absolute value functions for these kind of situations as well. Next is asking what graphs, key attributes, and characteristics are unique to absolute value functions. So the first one is the form of the graph, that we know that the graph always looks like a V. So that's the V form of the graph. That's the first characteristic or key attributes. And the next one is the constant slopes. As you look at the graph, like this example, we see that the two sides of the graph, there are two lines. They both have constant slopes, and one of them is positive. This one is positive, and this one on the left side is negative. So these are the two key attributes of absolute value functions. And this was today's lesson, and have a good day.